Let's get started. We want to explore continuous time. This is a time we live in the physical reality of the world. And this we will contrast to discrete time, the time that lives inside a computer. Module 6, Interpolation and Sampling. The outline of the module is the following. First, we look at continuous time signals, namely signals that live in the real world that we inhabit every day. Then we look at how to go from a sequence, the elements we have seen so far, into continuous time signals, and that's done through interpolation. Then we look at sampling, the cornerstone result here of this module, how to go from a continuous time signal to a sequence, and under which conditions this is a faithful representation of the continuous time signal. This will involve to look at aliasing, nasty phenomenon that we need to understand. Then we look at interpolation and sampling in practice. Finally, we look at the most important application, which is discrete time processing of continuous time signals. This is when we take a signal from the real world, we process it in a computer, and we render the signal into the real world. Module 6.1. The continuous time paradigm. First, we look at some models of the world and compare digital with analog views of the world. Then we study continuous time signals in some detail. We also introduce a continuous time Fourier transform, which is the last form of Fourier transform we have not encountered yet, and therefore this is a time to meet this very interesting mathematical object. We have seen these pictures before. These are the two views of the world. On the left, you see the analog world, the one we live in, and it's shown by a picture of the Earth taken by the Apollo mission. On the right side, you have a digital view of the world. This is taken by a digital camera, then very strongly pixelized, and the values are actually also discrete. So this is the view that you have of the world inside a computer. In short, this is a contrast between an analog continuous view versus a discrete and digital view of the world. We can show this in a block diagram form. We live in an analog world, so input and output are from and to the analog world, but inside we process on a computer which is discrete time. The input is x of t, the output is y of t, but inside the box we process sequences x of n, y of n. Examples of such boxes are, for example, the processing we do for MP3 music or what we do on a digital camera. Other examples are the following. You have a digital world, for example, you synthesize an image and you process it and then show it on a computer screen. This is a typical example in computer graphics or in video games. So the input to the box is a sequence, it is processed into an output which is a continuous time or continuous space image. Sometimes the box is used to take a decision. So the input is analog from the analog world, the output is discrete, for example, to decide something, should we take an action or not. The processing again inside the box is done on sequences xn from the input, yn to the output. This is typical, for example, in monitoring applications, is a certain level of temperature reached, and therefore in control systems. Let's summarize. The digital worldview is the one of arithmetic, of combinatorics, what is usually referred to as computer science, but also the world of discrete signal processing. The analog view is a view of calculus, integrals, and so on, distribution, system theory, continuous time, analog electronics. So you can see these are two sides of a coin, because we always have to deal with one and the other when we want to process signals in the real world. To make it slightly more mathematical, the digital view is you have a countable index, so xn, where n is an integer. So we have sequences, and we like to have sequences that are square summable, so xn is an L2 of z. We have a frequency that is limited between minus pi and pi, and we have a Fourier transform called the discrete time Fourier transform, which maps from L2 of z to capital L2 of minus pi to pi. The analog worldview is that we have a real time in second, t is measured in seconds, we have functions on the real line x of t, we like them square summable, that's what we call capital L2 of r. The frequency is given in radians per second and is unlimited, unlike in the discrete time case, and we have a Fourier transform that maps L2 of R functions into L2 of R functions, as we will see shortly. So how do we bridge the gap between these two worlds? So here's an example where we have, for example, computer synthesis generates a sequence xn. We have a sound card on a computer. This sound card has a system clock, so every ts second it will generate an output based on xn, and this output will be driving a loudspeaker. In the other direction, you are speaking into a microphone like I do right now. There is a sound card, it has a system clock, again with a sampling interval ts, and we get samples xn based on what was measured by the microphone. So we can see that there is a very intimate relationship between going from continuous time xt to xn, the sequence, that's called sampling, or from xn, a sequence, to x of t, that's called interpolation. And we have to be able to understand very clearly when we can go from one to the other, when these two are tightly related or they are not faithful images of each other. So let's study continuous time for a while. This is a new object because we have looked only at sequences so far. So we have a real-time variable t, we have a signal x of t, which is typically a complex function of that real variable t. As announced, we like them to be of finite energy, so the square integral of x of t is finite, and on L2 of R we can very naturally define an inner product between two functions x of t, y of t, as the integral of x star of t, y of t dt. And here x star, of course, is the conjugate of x of t, it's a complex conjugation. The energy is defined as the inner product of x with itself. We have just spent a module studying discrete time filtering. So naturally, there are also continuous time filters. These are called analog linear time invariant filters. They are given by a box H. The notation is x star H is a convolution. This can be written as an inner product or conveniently as the integral from minus infinity to infinity of x tau H of t minus tau d tau. Please note, very importantly, is the t minus tau, so that corresponds to a time reversal when you compute this integral. We promised a Fourier transform for continuous time signals. Remember, in discrete time, there was this maximum angular frequency of plus minus pi. In continuous time, there will be no such maximum frequency. It can go off to infinity. So the concept of frequency is the same. We take an inner product between the function xt and e to the minus j omega t dt. Now this is a capital omega. To be sure, we understand this is a continuous time Fourier transform. So capital X of g, capital omega is such a Fourier transform. We can invert this Fourier transform by renormalizing with 1 over 2 pi, taking the integral of the Fourier transform with respect to e to the j capital omega t. We will not study in great detail the conditions, when it exists, under what conditions it will converge, etc. But let us assume, for the sake of practicality, that this transform for the object of interest for us does actually exist. So this real-world frequency is very important because it does interact with what we have an intuition for. Capital omega is expressed in radians per second. We can also talk about hertz. That would be capital omega divided by 2 pi. So a hertz is 1 over seconds. And the period is 1 over the frequency in hertz, or 2 pi over capital omega. Let's look at an example. This is a good old Gaussian bell-shaped curve. So x of t is this exponential of t square normalized by sigma square, and it has the usual look. Its continuous time Fourier transform happens to be also a bell-shaped curve, simply rescaled appropriately. This is rather an oddity. Usually the Fourier transform of a function doesn't look like itself, as we will see in the sequel. We have seen the convolution theorem for discrete time convolution. The very same theorem holds for continuous time as well. So if we have x of t convolved with h leading to y of t, its Fourier transform is simply the product of the two Fourier transforms capital X and capital H. We introduce a new concept, namely the concept of band-limited functions. omega n bandlimitedness means that the Fourier transform of a function that is bandlimited is strictly zero outside an interval from minus capital omega n to capital omega n. This is a very simple function. It's a Rec function between minus omega n and omega n, centered around 0, and of height capital G. So this was the Fourier transform of this bandlimited function, the prototype of a bandlimited function. What is the time domain function? Capital phi is a Rec function, so phi of t is going to be the inverse continuous time Fourier transform, written here. We had calculated this in module 5.5, so let's not do it again. Please look it up if you don't remember it. And the time domain function is up to a scaling, one of these sinc functions. We will normalize this sinc function so that the area is equal to 2 pi in the Fourier transform domain. Then the inverse continuous time Fourier transform will have a maximum of 1 at the origin. So let's pick this. G is equal to pi over capital omega n. The total bandwidth is 2 capital omega n, and we define Ts as 2 pi divided by the bandwidth, or that's equivalently pi over capital omega n, and that will be a very important sampling interval for this sinc function. So now we have this prototypical bandlimited function. On the one hand, capital phi is the Rec function, and phi of t is the sinc function t over capital Ts. We see it now in normalized fashion, so it's a box function from minus capital omega to capital omega. The height is pi over capital omega. Its time domain function phi of t has a maximum at the origin equal to 1, and it has 0 crossings at multiples of Ts.